let's see how the state can be estimated. That is the concept of observers. I will talk about, for this part, the concept of observers, and then talk about the continuous time design as well as the discrete time design. Then all these, as a big picture, is going to give us, if we have AX plus B, if we have the state space system that look like this, and let's say we already know like the power of state feedback control. Let's say we want to design a state feedback law, all right? But we don't have all the state. We only can see the output. So these observers, they are going to give me, they are going to give us the alternative, the next best thing about the state feedback design. Instead of a full state, we do a state estimate. Okay, so we use an estimated version of the state coming out of the observers. So we're going to spend time for this observer state feedback and see, can we still do arbitrary pole placement or not? This connects to so many excellent topics in control systems. So the estimation problems, if we don't have noises, if we don't have random disturbances in the system, in the deterministic case, this is called observer design. And in the stochastic case, if we have like random disturbances going into the system, or maybe the measurement had some noise, then this is going to the concept of Kalman filter, one of the most known technique in not just controls, but also signal processing, but also a lot of computer science problems. All right. This problem, state estimation problem, is motivated by the fact that state feedback is usually, full state feedback is not available. So let's start with the easy case. Let's say we have a continuous time system. We have A, B, C, D matrices like this. X dot is AX plus BU. The most straightforward way to estimate X is perhaps this, right? So I'm going to make a copy of the system dynamics, use the same A and B matrix, then do this estimation. I run the state estimate just as parallel to the system actual state dynamics. All right? It has to start with somewhere, right? So let's say we have a guess. Let's try to guess the best of the estimate. We start the estimation from somewhere. Let's say x hat 0. If we don't know anything about the initial state, usually we choose at 0. Let's take a look at how the difference between my actual state and my estimated state will evolve. All right? This is just about the difference between these two state equations. So if I take a look at the difference, the derivative of E is going to be the derivative of x minus the derivative of x hat. So E dot is going to be equal to A times x minus x hat, which is E, plus BU minus BU. So the aerodynamics for this open loop observer, right, there's nothing feedback inside involved, is E dot equals AE. So some immediate observations can be made. If A is unstable, if the eigenvalues of A are on the left-hand side, some of the eigenvalues are on the right-hand side, then you will have trouble, right? The aerodynamics E dot equal to AE, then it's going to become unstable, right? Some of the arrows is going to blow up. That's not the only problem that can happen. The other problem that can happen is that if there are any input disturbances, right? If the actual system dynamics, there is an actual term, disturbance term, let's say WT, then WT is going to appear inside here, right? So this is a disturbance term, so there's no good measure usually for general disturbances in the observer. So we leave it as AX hat plus BU. So this disturbance term is going to propagate in the aerodynamics. So it can be sensitive to input disturbances. Because of these two facts, this open loop observer looks simple, looks innocent, but it actually does not usually work in practice. So the same will happen to the discrete time case. So you can do the same analogous. So everything will carry out exactly similarly. So we have the aerodynamics EK plus 1 is this minus this, going to be equal to A x minus x hat at k, right? So you're going to have the same problem if A contains eigenvalues outside of the unit circle in the discrete time case, then the aerodynamics will not be stable. All right, so what can we do then if we want to correct some of these challenges? So the quick thing, let's start with the continuous time. In the continuous time, the difference, the actual step that we can do to mitigate the challenges is this. So in addition to what we have done in the open loop observer, let's create a feedback mechanism. Let's say we take a look at the difference between the actual output and the estimated output. All right? So if I'm doing a good job in terms of observer design, if I'm estimating the state very accurately, then I would imagine the actual output to be similar to the predicted output. Now, if there are some errors, then I would expect this correction term is going to catch up those errors. All right? This is called the Luenberger Observer. So it has the correction term based on the output difference. So if we do that, then we can see that the observer, if we combine a few terms together, it's going to be A minus LC times X hat plus L times Y plus B times U. All right? Similarly, let's take a look at how the arrow is going to converge. So the aerodynamics, again, is going to be the difference between this equation and then this equation. So in other words, let's see, E dot is therefore X hat minus X dot minus X hat dot is AX plus BU minus this term, A minus LC X hat minus LY minus BU. All right, so the input term is going to cancel out as the same. And then for this part, so we can see that L times Y is LC, so Y is CX, right? So we have, therefore, A, this is the X term, this is another X term, so it's going to become A minus LC X minus A minus LC X hat. All right? It is therefore A minus LC times X minus X hat, which is E. This is the observer eigenvalue. This is how the error of the observer is going to evolve. Now we have some controls, right? So we can control the observer aerodynamics by designing this correction term, the gain of this correction term, to be more specific. All right, so it's A minus LC. If all the eigenvalues are on the left half plane, then we can see the aerodynamics it can be made arbitrarily asymptotically stable. All right, so this looks very much similar to the state feedback control problem that we talked about, where we were designing K, we were designing the feedback gain K to change the eigenvalue of this A minus BK matrix. And in the observer case is A minus LC. It's a we talked about duality between controllability and observability, and they show up a little bit in here as well. So let's take a look at the core result. Similar to the state feedback gain design, we have the following fact. If AC is observable, if the observability matrix constructed with A and C is non-singular, then all the eigenvalues of A minus LC can be arbitrarily assigned. All right? So the only requirement is that they are symmetric with respect to the real axis of the complex plane, right? So what we mean is that the eigenvalues, they always appear in pairs if they are complex, right? So they should be symmetric with respect to the real axis. So we're going to start by the case when A and C are in observable canonical form, and then we're going to generalize to the case when it is not, it's observable but not in observable canonical form. That is a simple step of similarity transform again. Our A matrix, therefore, is observable canonical form, is a lot of ones, and then in the first column we have these coefficients of the closed loop characteristic polynomials alpha 0 to alpha n minus 1. So that's for A matrix, and for C matrix we have this simple structure of 1 and then all zeros. All right, so what we want, keep in mind, is to be able to design L to place the eigenvalues of A minus LC, right? Let's say we want to place the eigenvalues somewhere at P1 to Pn. And we can write out this means that the determinant of Si minus A minus LC should be Sn gamma n minus 1. Let's put bars on top of these to indicate that they are for the observer case. Let's say the observer gain that we design, so the observer dynamics, keep in mind how the structure looks like, is Ax hat plus Bu plus L y minus Cx hat. So if it is single input, single output system, the dimensions are, this is going to be a vector, and then x or y is going to be a scalar. So L is therefore going to be a column vector. So let's say the column vector is L0, the coefficients are L0, L1, all the way to Ln minus 1. Then let's talk about A minus LC. So here comes the interesting fact again. Because C has this special structure, L times C will be very easy to compute. is only going to be, put out this calculation, it's L0 times 1 and then all the way 0 to the end for the first row. Same thing for the remaining rows, it's going to be L0, L1, all the way to Ln minus 1, and then 0 all the way for the remaining of the columns. So comparing this with the structure of the A matrix in observable canonical form, then we can get so this is the A matrix in observable canonical form. So we can see that A minus LC, it is not going to change any of the columns starting from the second column. So all these going to remain. The only thing that changes is the first column. A minus LC is therefore negative alpha n minus 1 minus L0, negative alpha n minus 2 minus L1, all the way to negative alpha 0 minus Ln minus 1. Recall that we know how the determinant, the eigenvalue of A looks like, right? So the determinant of the Si minus A is going to be all these coefficients in the first column shows up, right? So comparing the structure of A and A minus LC, then you can see the determinant of Si minus A minus LC, therefore, should be, the coefficients should all come from the first column. So it's going to be alpha n minus 1 plus L0. So be a little bit careful. This is alpha n minus 1 and L0, different from the state feedback case. And then all the way to alpha 0 plus Ln minus 1. So if we want to design the closed loop, the observer pose to somewhere, let's say the target polynomial, characteristic polynomial is gamma 0 all the way to gamma n minus 1, then you should design your observer L0, Ln minus 1 by, let's say from here, L0 should be gamma bar n minus 1 minus alpha n minus 1. And then Ln minus 1 should be gamma 0 minus alpha 0. All right? So that is the benefit. That is the powerful result we can do if we want to do observer design when the system is in observable canonical form. Let's also see the case if the system is not in observable canonical form. So we can do, now this time let's go a little bit into the details just to show you how we can do, how this similarity transform can actually help us. So we can transform the system into observable canonical form by this similarity transform. Let's do x equal to R inverse x observable, XOB. So the state dynamics is going to become, after you do this similarity transform, x dot OB equal to R A R inverse. This is the new A matrix plus R times B times U. All right? Just substitute x equal to R inverse OB, XOB here, then you're going to get the result. And similarly for y, let's do the case y equal to Cx. It's going to become, the new C matrix is going to become C times R inverse. All right, those are the structures that we are looking at. This one is in observable canonical form. So in observable canonical form, and the left-hand side is just a general observable system. So we know how to do the design if it's in observable canonical form. We have these beautiful formulas about how to design the observer gains L. So we can do this, use these previous formulas to design the observer gain L in this OCF form. It's going to be estimation x hat observable dot equal to A observable, this new A matrix, minus the observable gain times the C matrix, then times x hat plus L tilde y plus B hat B0U, this new B matrix. So do this design, which we know how to do in observable canonical form. We know how to choose these observer gains. Correspondingly, in the original state space, this is where we're going to implement the actual observer design. Let's see how the observer should look like. This is just going backwards, right? So we have go from here to here, and we've designed something from in this domain. Let's go back to the given system dynamics. So the relationship is just going reversely. X hat observable based on this relationship should be R times X hat. All right. What this design actually means is therefore, so replace XOB with R times X. We got R X hat. And then inside, you're going to have, so A, now put all these definitions of the A matrix into here. So it's R inverse minus L tilde times C0, it's C times R inverse. And then XOB is R times X. Then plus L tilde Y plus B0U, so it's RBU. All right, just put this design using a different set of notation. So then we can see that just some simple algebra. We can see this corresponds to, in the original, this is giving us a observer, right? If you take a look at the notation, it's X hat. This gives us a observer in the original state space. So read it out, it's X hat dot equals, so it's R, this R and this R is going to cancel out. We have an R inverse, it's going to cancel out with this R and this A. And then this R inverse cancels out with this R. So it's A minus R. So we put an R inverse here. This R inverse is going to go to L tilde. So it's R inverse L tilde times C. And then this R cancels out with this R inverse. So therefore, we have this. X hat dot is going to equal to A minus this part, some term minus C, right? So this is the L gain. This is the observer gain that we should implement in this original state space. So design L tilde based on what we discussed, these nice formulas, and then when you implement in this original system, implement it as L equal to R inverse L tilde. In the block diagram, this is how it would look like. So x dot equal to ax plus bu. That relates us to x dot equal to a times x. So x dot after integration becomes x, so x dot should equal to, in the original system, equal to a times x plus b times u. This is the state dynamics. X dot equal to ax bu. And then y should equal to x times c. This is how the state system can be realized. And then what the observer is trying to do is as follows. It takes the same input, goes through B, right? It's over here. And then it's going to have a structure that looks very similar to here. We're going to have the observer, observed state x hat, which is integrated from x hat dot. And x hat dot equals to bu, right over here, plus the first part, let's write it this way. So x hat dot equal to a minus lc times x hat plus ly plus bu. All right? Or in another way, you can write it as it's a copy of the original system dynamics, ax hat plus bu, and then plus the correction term. So x hat dot is ax hat plus bu plus this correction term. We have x dot hat here, so it's ax hat here plus bu, and then plus the difference between this actual output y and c times x hat, the estimated output y hat. All right, so it's plus this difference multiplying L and then go into this summation. So that is how an observer is built, how it's implemented in Simulink, for example. So that's the analysis form. This is the implementation form. So when we implement, we just compute L equals R inverse times L tilde. As a quick summary, if we are giving a system dynamics that look like this, and then we talked about the observer, closed loop observer, using a correction term, and the dynamics of the error. The overall system, let's talk about the overall system first. So the overall system contains two dynamic components. One is the state evolution x, and the other is the evolution of the estimated state. So it's going to be equal to x hat, so the new state of the overall system is going to contain two parts. First part is x dot equal to ax plus bu. And then the second part, x hat dot, is going to be, let's take a look. So x hat dot is a minus lc times x hat plus bu over here, and then plus L times y. And y is given the system dynamics, so it should be equal to L times c, x. So the observer depends on the observed state as well as the actual system state. So we can write it out as x hat dot equal to LC times x in matrix form plus A minus LC times x hat. So that is the augmented system, overall system. Now, when we talk about a state feedback control, we talked about the eigenvalues in that case. Now, let's take a look at the eigenvalue of the overall system right over here. Okay? So let us see how the eigenvalues actually going to distribute in this augmented system. Note that we can write the system in a different way. If you think from the perspective of the arrows, then we can treat the state space in this combination. So we can treat X and E as a set of new state. All right. The main motivation is that if you do this compared to that one, we can included all the essential informations, right? So this is E contains all the information about X hat. And then the similarity transform is indeed also invertible. We have this matrix, similarity transform matrix, that is invertible. So this is rigorous, this is legitimate similarity transform. If you see that we can actually represent the system dynamics with X and E without loss of information in the A matrix, then we can see that the overall system dynamics is nothing but this, right? So X dot is the same as AX plus BU. And we talked about the aerodynamics that E dot actually is amazingly simple. E dot is A minus LC times E, right? So E dot in the state space is 0 times X plus A minus LC times E plus 0 times U. From this A matrix, overall A matrix, we can see clearly how the eigenvalues are distributed. We can see that the eigenvalue of the overall system, part of it comes from the eigenvalue of A, which is whatever the system dynamics give us. And then the second part comes from the observer. So A minus LC is the observer eigenvalue, the observer dynamics. So whatever eigenvalue you design for the observer is going to go into this overall system. So that is the distribution of the eigenvalues. So all those are for continuous time. Let's touch upon the discrete time as well, similar to our previous analyses. We can build using the same concept. Observer should have a copy of the original system dynamics, and then it has a correction term. That compares the difference between the actual output and the observed estimated output. All right. So we're gonna see again the aerodynamics, how it's gonna look like. This is again very easy. So aerodynamics, just to subtract these two equations, we're gonna get E k plus 1 equal to all these terms are going to cancel out, equals to this term is going to cancel out, and then inside it's A, X minus X hat is EK, minus L times, so look at here, YK is CXK. So this is nothing but minus L times CEK. So the aerodynamics have exactly the same structure, A minus LC over here. We talked about if the system A and C matrices, they are in observable canonical form, then all the eigenvalues of this matrix can be arbitrarily assigned. So exactly the same thing. All right, this is the standard form, a full state observer. Now, if you go to move on to take a look at Kalman filters, it involves one more extra step. The main observation to make is that if you take a look at this is so-called full state observer, but with a predictor inside. It is motivated by the fact, see here, if we have the regular observer update laws, so x hat k plus 1 is ax hat plus bu plus y l yk minus cx hat k. This update law, if you think about it, when we do that when we want to update and compute the state at k plus 1 time instance, right? But the equation that you see here, we are looking at time k plus 1, and we are using the information, we are using all the measurements up to time k, right? We're not using the most recent update, meaning that after we collect the new measurement k plus 1, we are not using it effectively in the state estimate. Although yk plus 1, you can imagine that it contains a lot of information about k plus 1, xk plus 1, right? So the concept of a discrete time observer with a predictor is to bring in this most recent output into the update law. It goes like this, saying, first we do a prediction. We use a copy of the open loop system dynamics to create an estimate. So this is to estimate at standing at after using everything up to time k. So that's the notation. So this one is estimate of x hat using every information possible up to time k. All right, so this is using A, the previous estimate, plus BUK. And then after we obtain this measurement, YK plus 1, then we do a correction. We do a corrector. So we bring in this most updated information at K plus 1 into here. So we correct this predicted value by using the most recent difference between the actual output y and the predicted output y at k plus 1. All right, so that's the concept. Prediction and correction using the most recent information. Formally, this is the x cat kk is estimate of xk based on all the measurements up to time k. And then if it's k minus 1, it's based on all the measurements up to time k minus 1. And then the estimation error is defined by xk minus x hat kk. This looks all intuitive and reasonable. Let's take a look at how the error looks like. So how the error would converge. So the aerodynamics can be written out, can be analyzed similarly as before. So let's see what we can do. Error is x minus x hat. Our x is, let's do the comparison. All right, so x looks like this. We want to analyze ek plus 1. We already have xk plus 1, so let's see how x hat k plus 1 given all the information up to k plus 1 will look like. So let's see. Put the first prediction into the second equation. Then we can see that x hat k plus 1 given information at k plus 1 should equal to, let's write it out, should equal to a x hat k. Let's do it in this way actually. So let's combine this term and this term first to get I minus LC x hat k plus 1 given k, and then plus L y k plus 1. Okay, so let's combine these first two terms first to get this, and then substitute into the predictor term. So the prediction equation going into here is going to become I minus LC times A x hat kk plus I minus LC times B times UK, and then plus L y k plus 1. So then let's do the subtraction. Let's do subtraction of equation 1 with equation 2 to get, let's see, so it's going to be AXK minus I minus LC A x hat k given k plus BU minus BUK minus I minus LC BUK minus LY k plus 1, so which is C times x k plus 1. All right. We have this, so it equals A. Let's take a look at this term. So this has an xk plus 1 term, so it's AXK minus LC times xk plus 1, so that's AXK plus BUK, and then minus I minus LC AX hat k given k plus BUK, and then minus I minus LC BUK. So we can see a lot of cancellations actually. We can see they both have I minus LC A, right? So I minus LC A minus LC A xk, I minus LC times A times xk plus 1. So we got xk minus x hat k given k. So that's all the terms about x. And then the terms about BUK, if you take a look, is actually quite straightforward. We're going to have BUK cancels out with I times BUK over here. And then the LCB UK is going to cancel out with the LCB UK. All right, so plus plus becomes minus minus becomes positive, and then cancels out with this negative term. The whole thing is therefore I minus LCA EK. So again, the aerodynamics is amazingly simple in structure. EK plus 1 equal to I minus LC times A. That's the aerodynamics. Let's take a look at how this aerodynamics look like. So it equals I minus LC times A, or if you want, we can write it as A minus LCA E. Okay, so A minus LCA EK. in the standard observer design, we have this A minus LC, right? So we talked about the principle that if this AC pair is observable, then we can place the eigenvalue of this matrix arbitrarily. For this case, we can see that this is, if I define this C times A as a new C tilde, then we can see that this is in the same structure, A minus L C tilde, compared to this. So if this pair A C tilde is observable, then we can do arbitrary eigenvalue assignment for the aerodynamics. So this is essentially also saying that ACA, because the definition of C tilde, ACA is observable. So that's the concept. Now let's just take a look at whether this matrix, when it would, this pair ACA will be observable. So if we write out the observability matrix, it's going to be C tilde, C tilde A, C tilde A n minus 1 all the way. And it would equal to, right, so just plug in C tilde. It's actually equal to the regular observability matrix times A. Okay? So if this matrix QD, observability matrix, has full column rank, and if A is invertible, you can see that QD tilde will have the same rank. So in that case, we're going to have observability. All right? So put in other words, if A is non-singular, it's invertible, and the pair AC is observable, then the discrete time full state observer with a predictor will be observable, and we can do arbitrary pole assignment for the observer dynamics. Okay? This condition that A is non-singular is not difficult to satisfy. For example, in the discretization, we talked about a continuous time system, AC, continuous time. After discretization, it's going to go to EAC and then sampling time delta t. So if A is obtained from discretization of a continuous time system, then this matrix is going to be invertible because it's in this structure. All right. Okay. We talked about observers. We talked about this big picture at the beginning. Right? We talked about this big picture. Now, with an observer, and if we still want to enjoy the benefit of a state feedback, then let's see what happens if we replace x with x hat in designing the control law. So that is the problem of observer state feedback. As a quick overview, this is for the problem, for the case when the full state are not available, and we want to figure out what is the performance we can achieve by combining state feedback and then observer design technologies. So the full closed loop system now becomes, so this is original system, x dot equals ax plus bu, y equals cx. This term, the design includes two steps: the observer design and observer state feedback. All right. Let's take a look at the closed loop dynamics. If we write it out directly, this is going to become, so plugging in the control law into the system equation and then the observer equation, then we can see x dot is a times x. Now here, b minus b times k times x hat, then minus bv plus bv. So in matrix form, so it's x dot equal to ax minus bk times x hat plus bv. And for the observer x hat, we're going to have x hat dot equal to ax hat minus bk x hat plus bv plus L times C, L times Y is L times Y equal to Cx, so it's LCx minus LCx hat. So it contains one term about x, and it contains three terms about x hat. So we can write it as LC times x, and then A minus LC minus BK times x hat, and then plus BV. All right, so this overall augmented closed loop system seems now we have a lot of non-zero terms in A matrix. But it turns out that we can also get a very clear picture of the closed loop eigenvalues by analyzing, again, just the aerodynamics. So this is again from the similarity transform by looking at the system state from X and E perspective. So we can see that the aerodynamics will be straightforward to compute. Okay, so you should be able to obtain, let's see, aerodynamics equal to x dot equal to x hat. Okay, so it will equal to a x minus x hat, then minus L y minus c x hat, or in other words, a times E minus L, y is cx minus cx hat. So it's a times E minus LC times E. So it's A minus LC times E. Exactly the same aerodynamics. All right? So we can write the system equation in this form. Therefore, on the top, it's the same. X is actually, we need to do a little bit of work here. So we have write out the relationship of E with E. So this is dE, E dot equal to A minus LC times E. We would still want to express X as a function of X and E in this new set of state. So let's see, X dot, right? So we know that is A x plus bu is ax minus this bk x hat plus bu. So we want to create a x as a function of x as x and e. So let's just do this. Ax, we already have x, and then let's figure out what x hat equals to. So e equals to x minus x hat. So therefore we know like x hat is x minus e, and then that should do the work. All right, so over here, then we have expressed x dot as x and e, functions of x and e. So it's a minus bk, x plus bke plus bv. All right, so it's a minus bk times x plus bke, then plus b times v. So the main thing, the key point that we can recognize is that this aerodynamics, as you can see, right? So it's separated into two submatrices. Okay, so the two submatrices are the two submatrices A minus BK and A minus LC, they're going to define the eigenvalues of this upper triangular matrix. If you take a look at the structure, so the first set of eigenvalues come from the eigenvalues of A minus BK, and the second set comes from eigenvalues A minus LC. Go one more step further. The eigenvalues of A minus BK, if you remember, this is the eigenvalue coming out of the state feedback control design. Right? So this is designing the state feedback law K. And then the eigenvalue of A minus LC is from the observer eigenvalue design. Right? So it's about designing of L. So this is a very nice separation if you think about it. It tells us almost as if you want to do observer state feedback, you can control the eigenvalue of the overall system by designing the state feedback separately from the observer. So you can design state feedback just as if you want to control a fully controllable AB matrix, right? And then you design the observer just as if you are doing a single observer design with A and C pair. Therefore, if system is controllable and observable, then that tells us we can do arbitrary eigenvalue placement of the closed loop, right? We can do arbitrary eigenvalue placement of this part and this part. Arbitrary eigenvalue placement of closed loop system. So that is the separation theorem, a very nice result that can give us independent designs of the state feedback and the observer. All right, today we talked about state feedback control design if we have access to all the state. We talked about state estimation if we don't have access to all the state. And then we talked about, finally, the powerful result of state feedback, combining the both of them. And we see the nice separation theorem.